Okay, so welcome to our seminar, Monday seminar. And it's our pleasure to have Adam Waterbury, new in the department. And so you'll be talking about asymptotics and approximation of quasi-stationary distributions. So Adam, the screen is yours.
All right, thank you. Thank you for inviting me to speak. This is my first year as a visiting professor at UCSB, and I just finished my PhD in May at University of North Carolina. And this is based on my dissertation work. So I'm going to quickly introduce the notion of quasi-stationary distributions for those of you who have not seen it before. And then I want to talk about two different papers that came out of my dissertation. One is dealing with asymptotics of quasi-stationary distributions, and the other is with numerical methods to approximate them. So the basic idea behind quasi-stationary distributions is that if you have an ecological model or a chemical model or a model in a lot of other different fields, if you want to make sure that it's fully realistic, the system might only persist for a finite period of time. So for instance, if you're modeling some ecological system where you're counting the number of some species, well, then after all of those species die off, then they won't be able to reproduce anymore, and so they'll be extinct. And if one is studying a system like this, the period of time that it takes for this extinction event or this absorption event to occur can be very, very long in the case of ecological models and things like that. But nevertheless, this extinction or absorption typically will still happen with probability 1 after a finite amount of time. And so if one is interested in understanding the stability of such a system prior to absorption or prior to extinction, then quasi-stationary distributions are the main mathematical tool for doing so. In order to introduce the notion of a QSD, we'll consider a Markov chain Xn, and we'll be doing everything on a countable space in this talk, which we'll denote by delta. And we're going to assume that the chain becomes absorbed when it hits some collection of states, d delta, which I'll just call the boundary. And then we'll denote the set of allowed states by delta interior. And for a couple of examples of what the boundary might represent in different contexts, in epidemiological models, the boundary might represent a disease being totally eradicated or the population having full immunity, because in either of these situations, the disease won't be able to spread anymore. In ecology, like I was saying, it typically will correspond to the extinction of one or more species. And there's also been contexts in finance and telecommunications and related fields or various other fields where QSD have been studied. The fundamental problem that leads to the need to study QSDs is that if you have a system that gets absorbed in the boundary in finite time, if you look at its stationary distribution, it's going to place all of its mass on the boundary. And so if you're interested in understanding the long-term behavior of the process prior to absorption, because that's when all of the interesting dynamics are going on, then stationary distributions aren't very useful for understanding that, because they simply say that in the long run, the chain will get absorbed. Oops. And so the way that we define a QSD, it's a probability measure on the set of allowed states that's defined or that satisfies this conditional evolution equation. So it's analogous to the definition of a stationary distribution. And I should point out that in the case when the underlying chain Xn is irreducible and aperiodic on the interior of the state space, then the QSD can be interpreted as a sort of limiting distribution of the type described here. So the first paper that I want to talk about describes a model of different interacting species that are evolving in the non-negative orthont of RD. And so the state space of our model is the non-negative orthont. And we're going to assume that our chains are absorbed when they hit the boundary, meaning when any one of the coordinates is 0. And we're going to be considering a collection of chains that are indexed by a scaling parameter capital N. And what this parameter capital N is going to do is describe sort of the size of the system. So as n increases, the size of the system increases with it. And I'll explain exactly how that happens. And so the idea is that the nth chain is a delta n valued random variable, which is defined recursively like this. Here, the etas are some random variables distributed according to some stochastic kernel, which is ultimately going to need to satisfy certain large deviations assumptions. And I just want to emphasize that the nth chain, xn, is absorbed in the boundary of delta n. Oh, and I should say, if anyone has any questions, please feel free to interrupt me. So since the chain is evolving in the non-negative orthont of RD, we can think of it as modeling a system with D subpopulations. And so the way that the scaling comes into play is if we look at the ith coordinate of the nth chain at the kth time instant and multiply it by n, that tells us the number of individuals of species I in the nth system at time k. And if you just recall the definition of the boundary in our setting, you can see that absorption in the boundary corresponds to the extinction of any one or more of the species. So we want to study the long-term stability of the system prior to any species going extinct. So we make some assumptions, like I alluded to earlier, on the large deviations properties of the kernels. I'm not going to get into those here, but we do make some further assumptions on the dynamics of the chains. So if we denote by x hat n, the continuous time process that we get from linearly interpolating between the different points of the discrete time chain, then we'll assume that on compact time intervals, the continuous time process x hat n converges to the solution of some ordinary differential equation as the system size tends to infinity. And here at the bottom, I say that the function g satisfies suitable stability conditions. It turns out that these stability conditions are actually really natural. And if we think of our system as modeling, a collection of species that are going to interact and persist for a long time. So the sorts of things that G needs to capture is that there needs to be it needs to have some drift away from the boundary. G needs to push the flow away from the boundary so as to encourage, extinction from not happening too rapidly. And G also needs to not grow without bound. That we need to assume that the species are not on average growing and continuing to grow indefinitely. So our second assumption is that for each chain, xn, there's a QSD mu n, and that the sequence of QSDs is relatively compact. The reason that we need to make this assumption is that since the state space is the non-negative orthont of RD, it's not compact. And so in general, chains like these may not have QSD. Though I will introduce a particular model where they do, where we prove that they do. Yeah. So the basic idea behind this work is that the continuous time process x hat n is a random perturbation of this underlying flow phi. And as the size of the system increases, the system tends to behave more and more like the underlying deterministic flow. And so our hope is that we can use dynamical systems properties describing the long-term behavior of the flow phi to understand the long-term stability of the chains prior to absorption. And so what we'll do is study the QSD as the system size tends to infinity. So similar results were established by Foray and Schreiber in the discrete time dynamical system setting. And one of the big differences between their work and ours is that they were considering a discrete time dynamical system that mapped into a compact space. And so since their system was essentially taking place in a compact space, there was no issue of arguing existence or tightness of QSD. And also the discrete time nature of the dynamical system made it easier for them to establish a global large deviations principle. And so in our work, we had to, for reasons relating to the moment generating functions of the kernels of eta, it's difficult to establish a global large deviations principle for the processes xn. And so to overcome that, we basically consider a collection of modified processes where we just continually project the process x hat or xn back into a compact set. So we reduce the problem of large deviations principle to large deviations principle of a process taking values in a compact set. And it turns out that that's enough for our analysis. And due to the unbounded nature of the state space, there's also some underlying difficulties that emerge when studying the long-term properties of the flow phi. So in order to, sorry, I have the pictures in front of the title of the slide. Yeah, so in order to state our results, it'll be helpful to introduce the notion of an absorption preserving pseudo-orbit. And so we call it an AP pseudo-orbit. And it's a collection of points Ci to Cn that essentially captures small perturbations of the underlying flow phi. So if you start at x, you can jump, then follow the flow for at least a fixed amount of time. And then you can jump a small distance again. And so it's not shocking that this notion might be helpful for studying what is essentially a random perturbation of the flow. And this notion of AP pseudoorbits introduces a equivalence relation on the interior of the state space. And essentially, if for every t and delta greater than 0, there is a delta t pseudoorbit from a point x to another point y, then we say that x leads to y in AP. And if x leads to y and y leads to x, then we say that they're equivalent under AP. And the reason that I need to introduce this definition is because our main results are stated in terms of these equivalence classes, which we call AP basic classes. And they're also stated in terms of maximal AP basic classes, which we'll call AP quasi-attractors. And so I'm not going to dwell on the exact definition of an AP pseudo-orbit or an AP quasi-attractor in this talk. And I think that the best way to think about AP quasi-attractors is that they're all interior stable fixed points of the underlying flow. And they're also attractors of the flow. So you can just think of them that way. And I think it's easier to follow. So our third main assumption is that there are a finite number of AP basic classes in the interior of the state space. And we'll denote those by Ki, where I goes from 1 to V. We'll assume that each Ki is closed and that for some L less than V, the first L Ki's are in fact quasi-attractors and the remaining ones are not. So again, these Ki for I equals 1 to L can be thought of as interior stable fixed points of the flow. So our third, or our main result says that under these assumptions and some additional large deviations assumptions, if mu is a weak limit point of the sequence of QSD, then it's invariant to the flow and it's supported on the union of the interior AP quasi-attractors. And additionally, if we look at lambda n, which describes the probability that the system persists for a fixed amount of time, then this lambda n converges exponentially to 1. So as the system size increases with higher and higher with exponentially high probability, the system will persist and not be absorbed for long time periods. And so, yeah, we can interpret this result as saying that the limit points of the QSD are supported on the union of the interior attractors of the flow. The basic idea behind the proof is that using some large deviations estimates by using a uniform large deviations principle on compact sets and studying the dynamical systems properties of the flow, we can show that limit points of the QSD do not charge the boundary. So they put all their mass on the interior of the state space. And then we can show that they're invariant under the flow. And this invariance is important because it allows us to apply a Poincare recurrence theorem to show that the limit points are in fact supported on the union of the interior AP basic classes. So I just want to point out, this is saying that the limit points are supported on the AP basic classes, but it's not saying that they're supported on the quasi-attractors themselves. And so what we need to do to complete the proof is show that if we have a AP recurrence class, which is a non-quasi-attractor, then the limiting measure doesn't put any mass on it. And it turns out that in order to show that the weak limit mu does not charge the non-AP quasi-attractors, it's helpful to formulate another equivalence relation and another sort of recurrence. This form of recurrence is formulated in terms of the quasi-potential associated with the large deviation principles rate functions. And essentially the way that it works is if you have a point X and a point Y, this quasi-potential will assign a cost to any path between X and Y. And this path is defined in terms of the local rate function from the large deviations principle, or the rate function from the large deviations principle, excuse me. And the idea is that if there are arbitrarily cheap paths between 2 points, then they belong to the same recurrence class. And so, for example, if the flow started at X leads to the point Y, then they will belong to the same recurrence class because the cost of the underlying flow phi is 0. Yeah, so that's a broad outline of of how we approach the proofs, and I want to talk about a slightly more concrete example. So we consider a collection of Markov chains, again, Xn, where capital N denotes the size of the system. And at each time step, any individual in any of the populations or any of the subpopulations dies with probability 1/n. And conditional on the population size at the previous time instant being nx. Again, this scaling is capturing the fact that nx describes the size of the population. Then the number of individuals of type I that are produced at the next time step follows a Poisson distribution, with whose rate is given by fi of the current state of the system. And so this is the more general framework that we consider, but there are some common models studied in ecology that fall into this framework. For instance, if one considers a stochastic version of the generalized Lotka-Volterra model, here we would have the fi of x is x times this mean reproduction rate plus this interaction effect. So here bi describes the rate at which species I reproduces when it's in isolation. So there's no interaction being described by bi. Aij is somehow capturing the interaction between species I and species j. And ci is basically saying, how large population I can become. Then our results recover a result that's well known in the dynamical systems literature, or they agree with a result that's well known in the dynamical systems literature, which is that the limiting measure mu puts all of its mass onto a point x naught, which is defined like this. Here, A is the matrix of interaction effects, and B is the vector of reproduction rates. Some significant challenges arise when one is trying to study the asymptotics of QSD in this Poisson binomial setting. Probably the biggest one is that since the state space is unbounded, it's not immediately obvious that QSD exist. And even if they do, it's not obvious that they're tight. Additionally, since the boundary consists of the states where any species has gone extinct, where at least one species has gone extinct, rather than where all species have gone extinct, that causes some additional difficulties as well. Because you can be really close to the boundary, in our case, and still have really, really large populations. As long as just one of the species is close to extinction, you'll be close to the boundary. And so it turns out that presents some difficulties too. So in order to verify the existence of QSD, we apply a relatively recent Lyapunov function-based criterion that was established by Champagnat and Villemonier. And in this case, our Lyapunov functions that we use to study the stability of the system are the exponential moments of hitting times of particular compact sets. So we argue that if you have a compact set near the origin, then its hitting time has exponential moments. And somehow these moments are uniform in the size of the system. Then using similar techniques and similar estimates that we obtain from these Lyapunov functions, we can also argue that the QSD sequence is tight. So the main takeaways from this paper are that we consider a collection of ecological models that describe interacting populations. And we're interested in understanding the long-term stability of these populations prior to any of the subpopulations going extinct. Quasi-stationary distributions are the fundamental mathematical tool that one can use to study, this pre-absorption stability. And so we're interested in the QSD of these systems. In particular, we're interested in what happens to the QSD as the size of the system increases. And what we show is that, as the size of the system tends to infinity, these QSD, which describe their long-term stability prior to absorption, can be described using the long-term behavior and dynamical systems properties of some underlying deterministic model. Yeah, and we can apply this framework to problems in ecology, and we can recover some of the well-known results. Before I move on to the second part of the talk, does anyone have any questions about anything that I've introduced so far? Okay, yeah, so then I'm going to move on to what I think is the more applied portion of the talk, and hopefully it's interesting. So this is about a paper of ours that we submitted. It's called, or it studies the approximation of quasi-stationary distributions with interacting reinforced random walks. And the main idea is that we introduce two new simulation approaches, or simulation-based approaches, that can be used to approximate the QSD of a finite state Markov chain. And so I'll talk about what these approaches are, some related approaches that inspired ours, and then I will conclude by showing you some brief numerical results. So the notation in this part of the talk is going to be similar to the first part, but things are going to have a slightly different meaning. So here, the state space delta is just some finite set from 0 to D, and we denote the absorbing state by, or we just assume the absorbing state is 0. And we'll denote the absorbing and allowed states using the same notation as before. And we'll consider a delta valued Markov chain Yn with some kernel Pxy that's absorbed at the boundary. And further, we'll assume that when we view the chain, the interior is an irreducible class of the chain, and that the chain can hit the boundary. So this irreducibility assumption is basically just saying that if the chain is in state X in the interior of the state space, then with positive probability, it can get to any other state Y in the interior of the state space. The accessibility assumption says that there is some X such that the probability that you jump to the boundary from X is positive. Under these assumptions, there's a unique QSD for the chain, and we'll denote this QSD by theta star. So using the definition of QSD and Perron-Frobenius theory, using Perron-Frobenius theory, one can actually argue the existence of a QSD in this setting. And one can show that it can be characterized as the left eigenvector corresponding to the leading eigenvalue of the transition matrix restricted to the interior of the state space. So here, P interior is just the transition matrix restricted to the set of allowed states. And this, the QSD satisfies this equation for some lambda in 0, 1. Additionally, using the Markov property and the definition of QSD, we can show that for this lambda, the probability that the chain persists for at least n, or for exactly n time instance, is lambda to the n. And so if we take n equals 1 in that, that calculation, we can see that lambda depends on theta star explicitly. So if we're attempting to solve equation 1, we need to simultaneously solve for theta star and solve for lambda. The issue with this is that the relationship between lambda and theta star in general is nonlinear in theta star, right? There's no reason that this probability should vary linearly in theta star. And this leads to problems when either the state space is large or when the underlying transition matrix is irregular or ill-conditioned. And this nonlinearity can make it difficult to solve the equation 1 to find the QSD and this eigenvalue lambda using deterministic numerical methods. So there's been a lot of research that's been done to study simulation-based approaches to solving equation 1. And these approaches can be divided into two main groups. The first is the use of Fleming-Vio particle systems. So in this approach, one considers a really large collection of particles. And it turns out that the number of particles that one considers should grow exponentially with the amount of time that the particles will evolve for. So it really is a large number of particles. And the way that these particle system approximations work is that one evolves the particles independently until a particle hits the boundary. And then once the particle hits the boundary, it instantaneously jumps back to the position of one of the other particles uniformly at random. And what one does is studies the empirical measure of these particles and their convergence results for these sort of approximations say that as the number of particles tends to infinity, and then as time tends to infinity, the empirical measure of the n particles at time t converges to the QSD of the system. And there's been some various rate of convergence results and central limit theorems that have been established for the rates at which these approximation methods converge to the QSD. The second main set of approaches was originally introduced in a paper by Aldous, Flannery, and Pallisois in 1988. And I'll call this either the Aldous approach, the Aldous scheme, or the reinforced random walk approach. But the idea here is that you have a single particle that evolves to the kernel of according to the kernel of the underlying Markov chain yn until it hits the boundary. Then once this particle hits the boundary, it jumps back to the interior of the state space according to the empirical measure of the chain up to that point. So if prior to absorption, the chain had spent a lot of time at one location, then after hitting the boundary, it would be more likely to jump back to that location. And it's worth pointing out that this reinforced random walk approach does not have Markovian dynamics, because when the particle hits the boundary, its next step will depend on its whole past history. And the basic idea behind the two approaches that I'll discuss here is that the reinforcement in the Aldous approach has a lot of beneficial properties, because it ensures that if you run the chain for a long enough time, then you'll get a good approximation for the QSD. On the other hand, the Fleming-Vio particle system allows one to, in some sense, more quickly explore the state space. if you have a bunch of particles, you can choose their initial distribution in such a way that they'll cover the state space in a shorter amount of time. And so what we'll do is consider two methods in which we evolve a large number of particles. The motivation behind why one wants to do this is that it allows you to more quickly explore the state space. But we will reinforce their transitions, unlike in the Fleming-Vio particle system scheme. And so the particles are all going to interact with one another whenever they hit the boundary of the state space. And the picture to keep in mind is that, or of the sort of setting in which this approach might be useful, is if some of the particles in our system get stuck in a state like X for a long time. So imagine that X is fairly attractive, and so particles tend to spend a long time there. Well, as long as some of the other particles are exploring the rest of the state space, the particles that are trapped in X will still continue to update their dynamics according to what the other particles have learned. So they're using the fact that there are multiple particles exploring the state space to continue to learn even while they're trapped. And so for states like X and Y, where particles tend to spend a long time, I'll refer to them as basins when we get to the numerical portion of this talk. But I really just mean, states like this. So in order to introduce our approximation methods, it'll be helpful to introduce a little bit of notation. So for each probability measure on the interior of the state space, we'll consider a kernel k nu, which is defined like this. And what this kernel describes is a Markov chain that evolves according to the underlying transition matrix P until it hits the boundary. Then once it hits the boundary, it immediately jumps back into the interior of the state space according to the probability measure nu. And based on our assumptions of the underlying absorbed chain yn, we know that for each nu, the kernel k nu will have an invariant distribution, which depends on nu, and we'll denote that by pi nu. And a simple calculation shows that the QSD, the unique QSD theta star, is the unique fixed point of pi. And it'll be helpful to identify the space of probability measures on 1 through D with the D-1 dimensional simplex S, and to define the map H by H of nu is pi of nu minus nu. And in an earlier work by Benaim and Cloez, they studied a lot of the properties of this map H, and they proved that it's smooth, it's infinitely differentiable, and its Jacobian matrix is Hurwitz. And by Hurwitz, I mean that each of the eigenvalues of the, sorry, I meant to turn off my email notifications. Each of the eigenvalues of the Jacobian matrix has a strictly negative real part. And so I need to introduce a little bit more notation in order to introduce our two approximation methods. We'll have a step size sequence, gamma n, which basically grows like 1 over n, or 1 over k, I wrote it here. And it has this extra factor of gamma star on top and n star on the bottom. I'll talk about the importance of gamma star later and what role it plays in establishing rates of convergence. And I'll just point out that the only role n star is playing is to ensure that our estimates are always proper probability measures, so that gamma k is always less than 1. That's all that it's there for. And so I guess I have a bullet point about this here, so I should mention it. As gamma star increases, we're somehow weighting the later time instance more heavily, and this will be important. The other piece of notation is a sequence of positive integers increasing to infinity, an. An is going to determine the number of particles in the system, and I will describe exactly how. So our first algorithm, which we'll call algorithm 1, has 2 parameters, n, which will specify the number of particles, and k. And it's a little bit unusual the way that we formulated this, but for each n, we're going to consider a system that starts off with AN particles. So here, the number of particles is specified before you run the system. And so at time k equals 0, the nth system starts with AN particles. And then as time passes, you'll always have AN particles, and they'll evolve in the manner that I'll describe in a minute. The second algorithm only has a single parameter, n. And the way that it works is it starts off with either a single particle or a finite fixed number of particles. And then as time progresses, branching events occur and more events get added to the system. And we just add the particles in such a way that at time n, there are AN particles. In this talk, I'll focus more on describing algorithm 1 and talking about its analysis, because I think it's a little bit more novel in that it has a certain array type structure due to the fact that there are two parameters. So there's a lot on this slide, but the main takeaways are that algorithm 1 is going to be described in terms of a collection of random variables, or a collection of reinforced chains, xi and k, that evolve in the interior of the state space. And we have AN particles. The position of the ith particle in this system at time k is denoted by xin k. And our estimate for the QSD at time k in this same system is denoted by theta nk. And you can you can initialize the particles according to any distribution you'd like. And we'll see a little bit of that in the numerical results. And so the dynamics of the particles are defined recursively according to this conditional evolution equation. And all that this is saying is that conditional on the whole past history of the system, each of the AN particles will evolve independently. And if it hits the boundary, then it will jump back into the interior of the state space according to the current estimate for the QSD. And the way that this is different than the approach introduced by Aldous is that here our estimate for the QSD is going to be composed of all of the past positions of all of the particles. And the way that we define our estimate for the QSD is using this recursive equation. And you can think that gamma k plus 1 is more or less like 1 over k, or 1 over k plus 1. And so in that case, we would just recover that theta nk plus 1 would be the empirical average of the previous k plus 1 positions of the AN particles. But by having a more general step size sequence gamma n, we can allow for different weighting schemes. And in order to write the evolution of our approximation as a stochastic approximation algorithm, it'll be helpful to introduce the noise array epsilon k, which is defined like this. And I'll just remind everyone that pi of theta nk, or in general pi of nu, is the invariant distribution of the chain that evolves to the kernel k of nu. So with epsilon defined like this, we can rewrite the evolution equation for the approximation algorithm like this, in the more familiar stochastic approximation form. And then, sorry, I'll just point out that this is describing the evolution in a system where the number of particles is still fixed. It's AN. So this is describing the evolution in time. And the interesting question arises when we ask, what happens as the number of particles and time simultaneously increase? And in particular, what can we say about the asymptotic behavior of the approximation, theta nn? So what theta nn is the approximation after n time instants in the system that starts off with a lot of particles, with AN particles. And so we want to understand what happens if we start off with a bunch of particles and run them for a long time. And yeah, I just want to emphasize that because I think the notation can be a little confusing. So our first main result regarding algorithm 1 shows that the approximation in the system with an particles after n time instance converges almost surely to the QSD as n tends to infinity. And it also establishes an almost sure upper bound on the rate of convergence to the QSD. And unlike the analysis of the Aldis scheme or of a lot of other stochastic approximation schemes, it turns out that these convergence rates are really important when we study the central limit theorem of this approximation scheme. A couple things that I want to point out are that the law of large numbers holds even if the number of particles in the nth system is n. So you can really have a lot of particles in this setting, and the law of large numbers still holds. And the way that the law of large numbers is formulated is that for each p in 0, 1, there is some beta that depends on p, such that, for some n naught beyond that point, the approximation method will converge to the QSD with a rate of a polynomial or k to the negative beta, I'll say. And so it's worth pointing out the interplay between beta and p. So the smaller that p is, the longer the time horizon that our law of large numbers gives rate of convergence on is, right? As p tends to 0, the interval or n to p converges to 0 as well. And so if you want to establish an upper bound on the rate of convergence over a very long time interval, you need to choose p to be small. But the downside is that if you decrease p, then in general you'll decrease beta. So you'll get a less tight bound on the rate of convergence. And what the law of large numbers is doing is establishing an upper bound on the rate of convergence to the QSD as time and the number of particles simultaneously increase. And it's sort of uniform in time, up to n to the p. The central limit theorem requires some additional assumptions on the sequence an and on the step size of the algorithm. And like I said, the Jacobian of h of theta star is Hurwitz, and so its eigenvalues all have strictly negative real parts, and so we can bound their real parts above by some negative L. And that'll be important because that shows up in the central limit theorem, which says that if the number of particles in the nth system is little o of n, and if gamma star is sufficiently large as compared to this bound for the eigenvalues L, then under the natural central limit scaling, we have convergence in distribution of the rescaled fluctuations around the QSD to a multivariate normal random variable with covariance matrix V. And we can characterize the covariance matrix V as the solution to this Lyapunov equation. Here, and I should say that this sort of Lyapunov equation shows up frequently when one is studying central limit theorems for stochastic approximation methods. Here you can interpret U star as essentially a covariance matrix for the restricted, or for the chain restricted to the interior of the state space. So I'll not say too much about the proof, but the basic idea is that we can rewrite the algorithm like this. So we can decompose the noise terms into an error array, which consists of martingale increments, and a remainder array, which consists of terms that are very small. And then we consider the linearized evolution array, mu nk, which is just our linearization of theta nk minus theta star. And since its recursion is linear, it's easier to analyze. And in particular, it's easier to prove or to study the central limit properties of it, of the linearized evolution array. And then we define a discrepancy array, which just measures the distance between theta, our approximation, and the QSD and the linearized evolution. And the central limit theorem has two steps. The first is to prove a central limit theorem for the sequence sigma n mu n n. Proving the central limit theorem involves establishing a conditional Lindeberg condition for the sequence and characterizing its covariance matrix. And we can actually prove this central limit theorem for the linearized evolution, even in the case when an equals n. So even if the number of particles is not little o of n, we can prove the same central limit theorem. But where the requirement that we need the number of particles in the nth system to be little o of n comes from is that we need that in order to show that the discrepancy sequence after rescaling converges in probability to 0. So I won't say much about the second algorithm. It's defined very similarly. The basic idea is that you start off with a single particle, you let that particle evolve until some branching event occurs. At that point, you add another particle into the system, however you'd like. A typical choice would be to add the new particle according to the previous estimate for the QSD. And then these particles evolve independently until they hit the boundary, and then they use the same reinforcement mechanism to jump back into the interior of the state space. And once more, we can write the evolution equation in the more familiar stochastic approximation form. In this case, or for this algorithm, we also established a central limit theorem and a law of large numbers. And I should point out that in order to prove these results, we assume that the number of particles grows like n to the zeta, or like square root of n, or something like that. We think that as long as a of n is little o of n, that these results hold. It's just that making this assumption on the number of particles makes a lot of the estimates a little bit easier to work with. So it's done mainly for convenience. Here we don't establish an upper bound for the rate of convergence. And the reason for that is that in this case, where we have the branching system, we actually don't need to leverage any rate of convergence results in order to prove the central limit theorem. So in this case, and this is more typical of these sorts of analyses, in order to prove the central limit theorem, it's enough to just have the approximation converges almost surely to the QSD. I'll quickly give a little bit of description of why we require the number of particles to be little o of n when proving the central limit theorems. And it's helpful to consider the case where we have an IID collection of Markov chains. So for each n, CNM is a Markov chain where m describes time. And let's imagine that they evolve on the interior of the state space according to some kernel, and their stationary distribution is theta star. If we look at the empirical average of all of the past positions of all of the particles, or all of the independent chains, and we call that theta tilde nm, then in this case, one can, using martingale central limit theorem or martingale difference central limit theorem techniques, one can show that the rescaled fluctuations converge to a normal random variable with a mean of 0 and a covariance matrix U star, which one can characterize. But if A of n grows like A star n, so if it's just big O of n, then the limit of the rescaled fluctuations around the stationary distribution does not have a mean of 0. Rather, it has a mean of alpha star, and we can characterize exactly what alpha star is. It is this quantity. And here, Q naught is the solution of a Poisson equation associated with K naught. And I should have written down exactly what that is. In an earlier version of this talk, I had a bit more details about the Poisson equations in our case. But the main takeaway is that we can write down in this simple case exactly what alpha star is. But it's not at all clear what it will be in our case, in the case of the interacting reinforced random walks. And so a few comments about where this non-zero mean may be coming from. Well, if we have a lot of particles, then there's going to be some additional variability in the finite time behavior of the approximation. So what we'll be getting if we look at just the finite time behavior of a lot of particles is an estimate for the probability that yn, or it'll get us, it'll converge to as the number of particles increases, it'll converge to the law of yn, conditioned on y not being absorbed by time n, if that makes sense. And so this finite time behavior causes problems that need to be accounted for by reducing the number of particles. And the finite time behavior also requires that we put more emphasis on later time instance. And it makes sense that we'll want to emphasize later time instance more heavily, because we know that our particles are going to behave better and better as time progresses, right? Because they're reinforcing their dynamics as they learn about the state space. And so by increasing gamma star in the definition of the step size sequence, we are more heavily emphasizing particles later time instance. And I want to just mention that the single particle central limit theorem for the Aldous scheme that Benaim and Clow has established requires only that gamma star is greater than L inverse over 2, where our central limit theorem requires that gamma star is greater than L inverse. And this is exactly because we need to emphasize later particles more heavily. So in the last couple of minutes, I just want to show a few numerical experiments. So I ran the single Aldous scheme with AN particles. So these particles are all totally independent. Oh, no, excuse me. The single scheme is a single particle that's evolved for a very long time. The independent scheme is AN independent Aldous schemes that are all ran for n time instance. The interacting scheme is our algorithm 1. The branching scheme is our algorithm 2. And the Fleming-Vio scheme is the Fleming-Vio particle approximation. And the way that we measure how long this one is ran for is slightly different, because the Fleming-Vio particle system requires that the number of particles grows exponentially with time in order to get a good approximation. So here we run the FV algorithm with eta of n particles for zeta n time steps, where their product is n times an, and eta grows exponentially with zeta. When one is in a situation where the underlying transition matrix is very simple, like this one, all of the methods converge very rapidly. But as soon as you start adding in multiple basins where particles can get trapped for a long time or for long time periods, significant differences start to emerge. And the simulations that I'll show you were all done with this underlying transition matrix. And so I'll just point out that 0 is the absorbing state and that there are 3 basins, states 2, 5, and 8. And you can just think that the states 2, 5, and 8 are attractive towards particles, and once particles land in them, they tend to stay for long time periods. So in the first simulation, I let A of n grow like n to the 0.75, and I let the initial states be chosen uniformly from the middle of the state space, from 4, 5, and 6. And we can see that the interacting scheme has some nice convergence properties here. And it starts to differentiate itself, even though this is a simple case where the interior of the state space only has 9 elements. And even though the Fleming-Vio particle system was ran with a sufficiently large number of particles, we can see that it still exhibited some significant asymptotic bias. Like this Fleming-Vio particle system, no matter how long you run it, is not going to converge to the QSD because there are not enough particles. And here's another picture where I just compared the independent scheme and the interacting scheme, just so that you can get a sense of how those two compare in some specific setting. And then here's another comparison where all of the particles start from state 5. And I'll just point out that this like lack of monotonicity in the approximations or in the distance to the QSD was a little bit surprising at first, But I think it's really just an artifact of the fact that all of this, or it is just an artifact of the initial distribution. So this lack of monotonicity is coming from the fact that all particles are starting from state 5. The main takeaway of our numerical results is just that if you have a setting where there are multiple basins where particles can get stuck, then somehow introducing these additional interactions between various particles can help get a quicker convergence to the QSD. We haven't done any theoretical comparison of the various algorithms. All of our comparisons are purely numerical, but they did line up with our expectations and our intuition about in which settings our algorithms would perform well compared to other methods. I'll briefly just, in the last minute, talk about a few more problems related to this work that I'm working on, or that I'm hoping to work on in the near future. I've been working on establishing a large deviations principle for the QSD approximation scheme introduced by Aldous. And so my hope is to study the large deviations properties of the Aldous algorithm with a single particle. The rates of convergence and central limit theorems are well understood and well studied, but the large deviations properties don't seem to have been established yet. And so I think that will be really nice. I'm also interested in applying our interacting reinforced random walk framework to other reinforcement-based optimization problems. So we use all of these particles that interact, with some occupation measure to estimate QSD, but the framework is a lot more general, and I think that a lot of our results and a lot of our proofs would go through and apply in other frameworks too. And so I'd be really interested to see to study some other sort of problems where we can apply these techniques to get a better convergence to whatever we're approximating. I'd also be interested in looking at, the different applications of QSD and models arising in mathematical finance, and in establishing some theoretical comparison of the QSD approximation methods, because everything we've done so far has purely been numerical. And it's not entirely clear what comparison one will be able to make, but I think it would be nice to have a more concrete understanding of when each algorithm outperforms each other one. Yeah, so I have a little bit about the large deviations, but I think that it probably makes sense just to end it here. So yeah, thank you all for your time. And please let me know if you have any questions.